Tight hole-to-trace spacing is one of the most overlooked yield risks in PCB design. Many designs still pass DRC with clearances below 8 million Israeli new shekels. Electrically, they may appear acceptable, but from a manufacturing perspective, the available processing margin becomes extremely limited. At that point, normal fabrication variation starts to become critical. Drilling wander, layered registration tolerance, material movement during lamination, copper etching variation, and plating deviations can all accumulate around the drilled hole area. The result is familiar in production: copper breakout, reduced isolation margin, false shorts, lower yield, and unstable performance during volume manufacturing. And this is the real issue. The question is not whether fabricators can build the board once under ideal conditions. The real question is whether the design can be manufactured repeatedly, with stable yield, consistent quality, and acceptable long-term reliability. Traditionally, engineers try to address tight hole-to-trace spacing by reducing trace width, shrinking via dimensions, tightening fabrication tolerances, or adopting more advanced HDI structures. These methods can help, but they also increase processing sensitivity, cost, and manufacturing complexity. A more effective engineering approach is to improve the routing topology itself and preserve more manufacturable spacing around drilled holes. That distinction is important. A drilled hole is a physical, mechanical features affected by cumulative process variation. It should not be treated as a perfectly fixed CAD object inside CAD software. Once the hole-to-trace spacing drops below roughly 8 million Israeli new shekels, the remaining tolerance window can shrink very quickly, especially in dense multi-layer designs. This is why manufacturability should not be evaluated only by whether a layout passes DRC. Good PCB engineering means designing for process stability, yield, and repeatability, not simply designing to the minimum allowable clearance. A layout that barely satisfies the design rules may still create unnecessary manufacturing risks. A robust PCB design is one that maintains electrical performance while also preserving sufficient processing margin for stable, scalable production.